Any questions before I get started on any administrative things here?
You said Saturday, but do you mean Friday?
I'll post it by the end of Saturday. I don't want to promise Friday. I'll try to get it ready on Friday. But our exam is not until next Friday, so hopefully it should still give you enough time. Okay, let's get started. So in our last lecture, we went over the derivation of the Clapeyron equation, and we discussed like how exactly we want to use the Clapeyron equation to solve for relationship of pressure and temperature along the liquid vapor line or the solid vapor line of this one component phase diagram. In this process, we made 3 approximations solving for the liquid gas or solid gas phase transfer, or stating the volume of the gas is way larger than the volume of liquid or solid. We're also stating the delta HM is remain constant along the line of phase transfer as long as we're away from the critical temperature. And we were assuming gases are behaving ideally to get this relationship. So using that relationship, we went over one example into like how to use the different boiling point and also the vapor pressure to derive the delta HM, or the enthalpy of vaporization, the molar enthalpy of vaporization for the liquid gas equilibrium. And let's see one more application is how to use like a table, a thermodynamic table, to estimate boiling point at a different pressure. So this should be a pretty straightforward plug-in number kind of question. I'm gonna just demonstrate like how to set up the problem when I see a question like this. So when we're looking at it, or saying use the data in table 7.1, so the data is provided, I'll ask you to estimate the boiling point of argon at 1.5 atm. So the way of reading the question, or saying the boiling point, so this tells us we're looking at a phase transfer of liquid vapor phase transfer. We can read the table to see what are the things we know, right? So by stating this is a liquid vapor phase transfer, we can write out this equation that's derived from the Clapeyron equation describing the liquid vapor phase transfer. So I can write that down to say, okay, I want to use this natural log of P2 over P1 roughly equals to negative delta HM over R 1 over T2 minus 1 over T1. All right, so this is what's in my mind when I'm reading this question. And then I read the thermodynamic table that was provided to see what are the things I know. So what are the things I know? For example, I know this question is asking for the boiling point at 1.5 atm. So let me just call this one the boiling point to be like T BP or T2. Let's say this one is T2 at P2 equals to 1.5 atm. And reading this table here will be like, okay, so if I know P2 and I want to solve for T2, there are a few things I need to read from the table, like what is my T1 P1 pair? So that can be my normal boiling point. And we're looking for argon. We're looking for a normal boiling point. Okay, so that's here. All right. So I have my normal boiling point. That is my T1 equals to 87.3. P1 equals to 1 atm. Reading the table, we also have the molar enthalpy of vaporization. So we know my delta HM equals to 6.53 kilojoule per mole. All right. So then looking at the actual equation, right, we have my P2, that's 1.5 atm. I know R is a constant, that's gas constant. T2 is what we're solving for. T1 is known, and P1 is also known. So everything else is known. We just plug in the numbers to solve for T2. Very straightforward. So far, so good? All right. And then from there, in addition to the liquid vapor, solid vapor phase transfer, we also care about the solid liquid phase transfer. So for the solid liquid phase transfer, likewise, we start from the Clapeyron equation, which is the dP over dt equals to the delta Hm over T delta Vm. So let's see how it changes for the solid liquid equilibrium or solid liquid phase transfer. So like what we did, right? So first thing we want to do is move the terms. So my dP is on the left-hand side and everything else is on the right-hand side because we want to express pressure as a function of temperature. So that's on the phase diagram. You always have pressure on the y-axis, temperature on the x-axis. So to do that, we do the integration. And on the left-hand side, that becomes integration of dP equals to integral of delta H. Now it's solid liquid equilibrium or phase transfer, so that's melting or fusion. Or I should write delta fusion H divided by temperature delta fusion Vm dt. Or it's the same thing as writing it as the integration of delta fusion Sm over delta fusion Vm dt. And the relationship here is just the change of entropy for a reversible phase transfer is delta S equals to delta H over T. So the approximation, like what we did before for the ideal gas approximation, in this case, we're also making an approximation. That is, when my change of pressure is small, that is, this one is within like 100 ATM or something. Like we'll make sure like it's a very clear number that the change of pressure is small. Let's say less than 100 ATM. We can assume that these like delta fusion of entropy or delta fusion of your enthalpy and delta fusion of your volume will all keep relatively constant. All right. So with that in hand, then it's straightforward to solve this integral, right? It's just either you have your P2 minus P1 is roughly equals to, or delta P, your delta fusion S over delta fusion V and T2 minus T1. So that's this one. Or you have delta P equals to P2 minus P1, roughly equals to the delta fusion of H over delta fusion of V and natural log of T2 over T1, which is this one. And that's because we have a temperature on here. I'm just going to write those equations on the board so we can use it for the next question. All right. So now let's look at a more comprehensive question of how to best use these relationships together to solve a real problem. Like, for example, if we read this question together, we're saying, given that the vapor pressure of SO2 solid is 1 torr and 177 K. So vapor pressure tells you this is a solid gas equilibrium and gives you two values for that solid gas equilibrium. It also gives you vapor pressure of SO2 liquid to be 33.4 torr and then 209.6 Kelvin at 100 torr. Well, nevertheless. So it's giving you 4 vapor pressure numbers of your solid SO2 and your liquid SO2. The question is asking you to find the temperature and pressure of the SO2 triple point. And you can state any approximation you're making, meaning like if we are using this equation, you want to state what are the 3 approximations we are making by using this equation. And what are those 3 approximations? We're saying the Vm of gas is way larger than the Vm of solid or liquid. We have gases are ideal. We also have that delta Hm is constant along the equilibrium line when we're away from the critical temperature. And if you were asking what are the approximation we're making here, we're saying when delta P is small, and by say small, or say like less than 100 atm, the delta fusion as the delta fusion H and delta fusion volume are all constant. All right, so these are the approximation we made. And when the question asks you to state the approximation, make sure you state this approximation if you're using this equation, if you're using the variation of the Clapeyron equation. But again, back to this question. Now, since we are talking about this vapor pressure, naturally, we're talking about the phase transfer, right? So it's natural to say like we want to talk about liquid gas equilibrium, solid gas equilibrium. So let's just write out that equation to say, okay, eventually we'll be using that equation that's derived coming from the Clapeyron equation. So we're looking at natural log of P2 over P1 roughly equal to negative delta Hm over R 1 over T2 minus 1 over T1. What else? We have 2 sets of vapor pressure. So that means if I plot everything onto a phase diagram, I will be able to use these sets of pressure temperature pair to solve for the enthalpy of vaporization or sublimation. So that means, well, what if we just plot it on my diagram and see what that looks like? So let's say on the y-axis, I have my pressure. On the x-axis, I have my temperature. And let's use the same unit that's given in the question. And let's focus on this one, the first one, which is the solid gas equilibrium first. Right, so when we're saying it's vapor pressure of the solid SO2, we're talking about the solid gas equilibrium. So there must be a point. Let's see, we start from 1 torr and 177 K. So this is my point 1. And my point 2 is like 10 torr and 195.8. All right, so if we're looking at this equilibrium, we're talking about on the top, That's my solid, and then on the bottom, that's my gas. So along this curve, that is my first piece of information we can solve for. That is, using the point between my point 1 to point 2, we can use this equation once to solve for delta HM of sublimation. All right. What else do we know? And then let's move on to the next piece of information. That is the vapor pressure of SO2 liquid at another two sets of temperature and pressure. So now we're looking at liquid-gas equilibrium. Right, the question is asking for triple point where all three phases are in equilibrium with each other. So we need information from all three phases. So let's write that out. So that means at some point of 33.4 and 209.6, like these are not to the actual, like the numbers are, obviously the axes are different scale, but it's okay. Like we're not computers, I can't plot it on the exact position. And then we have 102 and 225.3, okay. So that's my point 3 and 4. And this one talks about the liquid and gas equilibrium. All right, so from 3 to 4, we can solve delta HM of vaporization. And what does the 4 diagram looks like? So that means in between the solid and liquid line, like if I somehow think about a connection between your point 2 and point 3, there must exist some kind of triple point where your liquid and solids will have the phase transfer, where all three of them are in equilibrium with each other. So the question is asking us to find what is this triple point. And thinking about how do we do it, right? So if we look at this point, between this point X to point 3, so that is again a liquid-gas equilibrium. So if we know what is delta HM vaporization, and we know the point 3, we'll be able to set up an equation with two unknowns, the T triple and P triple unknown for X. Likewise, going the backwards, between your X to 2, you have an equation with T triple and P triple unknown, and you have the T2 and P2 known, also with the delta H sublimation. Right? So by setting up these two sets of equation, we'll be able to solve for what is that triple point. So that's basically, this is just me going over how I am thinking about the problem, right? So in this case, now we have two equations, we have two unknowns, we'll be able to solve it. And let's see how do we do it. So I'm gonna do that on the board here. So step 1, we're solving for delta HM of sublimation and vaporization. So step 1, we're focusing on point 1 to 2. What we have is, again, the logarithm of P2 over P1. That equals to the negative sublimation of your molar enthalpy over your gas constant and 1 over T2 minus 1 over T1. Right, so in this case, my P2, T2 is known, P1, T1 is known. We just plug in the numbers here. And that becomes logarithm of 10 over 1, roughly equals to negative delta sublimation of molar enthalpy over 8.314 times 1 over 195.8 minus 1 over 177. So plugging your calculator, you'll be able to get the delta sublimation enthalpy equals to 35290 joule per mole. So we're using the same unit for your gas constant. It doesn't matter which version of the gas constant you use. So that's step one. Step two, now we're focusing on my point 3 to 4 to solve for the enthalpy, molar enthalpy of vaporization. So the same equation here, right? So in this case, we're looking at the natural log of 100 over 33.4, roughly equal to negative delta vaporization of molar enthalpy, 8.314, plugging the numbers, 225.3 minus 1 over 209.6. Likewise, plugging the calculator, you get a number of delta vaporization enthalpy equals to 27400 joule per mole. So from here, again, using the same equation, now thinking about at point X, we have two unknown, right? We have T triple unknown or Tx unknown, and we have Px unknown. So in that case, we can plug in what we know here, that is the logarithm of my pressure x P triple over my second point, which is P2, which is 10, now roughly equals to the negative of this number over 8.314 times 1 over, this is my T triple, or Tx, minus 1 over 195.8. So that's my equation 1. Equation 2, likewise, we're trying to set it up between point X and point 3 for my liquid-gas equilibrium. So that becomes my natural log of my 100 over the P triple. You can also use the 33.4. I just used 100 on my lecture notes for some reason. It'll give you the same answer. This one is Px roughly equals to the negative 27400, 8.314 times 1 over 225.3 minus 1 over Px. All right, so these two are the equation we set up. And now we have two unknowns, we have two equations. And then it becomes a simple math problem in how to solve it. You have multiple ways to do it. I mean, I like to think about it as like, what if I just add them together? So you have Px and Px both on top and on below of the natural log. So if I add them together, then the Px cancel out. It's just a math problem. So if we're doing that, we can say I'm adding my equation 1 and 2, that's my equation 1 and 2 together. So that becomes my addition of my natural log of Px over 10 plus, or inside the natural log, becomes 100 over Px. And on the right-hand side, we're adding them together. That's a negative 35290 divided by 8.314 times 1 over Tx minus 1 over 195.8 and plus this term here, 27400, 8.314, 1 over 225.3 minus 1 over Tx. Right, so the Px and Px will cancel out, and then you can use this equation to solve for Tx. I'll give you the number here. So here the Tx is 200 Kelvin. And later on, you can plug in this Tx into both of the equation and see if your Px comes out to be the same number as a sanity check. They should. All right. So I hope this is a quick demonstration in like, when you're reading a question that seems vague and seems like we never done it before, try to think about how do we translate an unknown problem into something that we already solved before, and so that we can use the equation we already derived. Okay, do you have any questions? No? Okay, sounds good. And that's all the new materials. All right, so that's all we want to cover for this entire quarter, and that's all you need to know for the final exam. And everything from now is just a review of what we discussed before. So I have like 20 minutes left. I want to do this conceptual roadmap with you, just to make sure you see how these topics are, after all, connected. Because we went over lots of things. We went over all the derivations, all the calculations, and it's very common of you working out of this class. It's like, I know how to plug in numbers into equations, but I have no idea what these numbers mean. So hopefully this will amend a little bit of that gap. So the structure of thermodynamics is, again, when we're talking about thermodynamics, remember, we're talking about a macroscopic phenomena. We're talking about more or less like volume, pressure, temperature. These are things that we can measure. These are macroscopic measurables. We're not talking about how does a chemical bond form or how does a chemical bond vibration is taking place. Those are more like quantum mechanical domain. So thermodynamics, pure classical mechanics. At the very beginning of our entire quarter, we start by looking at vocabularies of thermodynamics. Now these vocabularies should be pretty straightforward to you, like system versus surrounding. What does adiabatic war mean? And when we're talking about a system being homogeneous versus heterogeneous, what does it mean? All right, so these are the simple vocabularies of thermodynamics. We start by talking about their definition, and we've been using those definitions or terminologies throughout the entire quarter. And then from this vocabulary of thermodynamics and also equation of state, like PV equals nRT, we then went over two fundamental laws of thermodynamics. Namely, in the first law of thermodynamics, we went over to say there exists a state function, which is internal energy. So for a closed system at rest, no external field, we're saying the internal energy du equals to dq plus dw, right? So that internal energy, or the infinitesimal change of internal energy of a system, must always equals to the infinitesimal change of energy in form of heat and work. The difference between heat and work will later be covered in chapter 3, when we talk about the second law of thermodynamics. That is, we use the second law of thermodynamics and the Carnot cycle to define a new state function called entropy, which is ds equals to dq reversible over temperature. So the concept of internal energy or enthalpy, these are relatively straightforward, right? We have H equals to U plus PV. They're a form of energy. It describes the internal things that's going on without having like a movement, or a heat transfer. The concept of entropy, on the other hand, we spend a lot of time discussing what is the physical meaning of entropy. Now, what is the physical meaning of entropy? Anyone want to take a guess? Remember, we did the simulation, right? You start from particles separated from each other, and now we allow these particles to move randomly. What does it do? It eventually get into the position where everything is mixed, right? So entropy, at the end of the day, is describing the probability of a thermodynamic state. So that's some kind of constant times natural log of probability plus a constant. And here, I'm just going to say this is probability. All right. And we linked entropy to the concept of equilibrium. That is, as stated in the second law of thermodynamics, your entropy of any system that's not at equilibrium will always increase, or the entropy of your isolated system always increase until it reaches an equilibrium. Let's say S time for an isolated system, and always increase until we reach the point that everything is at equilibrium. So here's a quick link to the concept of cosmology, right? What's the fate of our universe eventually after infinite amount of time? That is, well, entropy will always increase for the entire universe until we reach a point that only reversible processes can take place, everything in equilibrium. And then, using the idea here of the entropy of an isolated system always increase, we later on defined two new state functions, the Gibbs free energy, G, and also the Helmholtz energy. So G is defined as H minus Ts, A is defined as U minus Ts. We care about these two new state functions because we want to have a description of material equilibrium. So what we end up saying is the Gibbs free energy, if you plot G as a function of time for this closed system, constant temperature and pressure, your Gibbs free energy will always decrease until it reaches the equilibrium. The physical meaning of the Gibbs free energy is that it tells you what's the maximum amount of non-PV work your system can output. All right, so PV work is the expansion and contraction of the system. Like typically we don't care about it. It's hard to use the PV work. We care more like magnetic work or electric work that we can utilize. Alternatively, if we're focusing on the Helmholtz energy, we have the same kind of relationship, but now this is closed, constant temperature and volume. All right, so the Helmholtz energy always decreases until we reach that material equilibrium at the end of the curve. So for all these state functions, so far we have U, we have H, and then we have entropy, we have Gibbs free energy, we have Helmholtz energy. We spend a good amount of time of our entire quarter talking about, first of all, what are them? How are they defined? And then how are they connected using thermodynamic relations? So that is your Gibbs equation, and then later on the Maxwell relations. How to express them into things that we can measure, and how to calculate the change of these state functions. Because after all, we care about the change of my state functions. You have two thermodynamic states, and I want to know if I change my thermodynamic state from like T1, P1, V1 into T2, P2, V2, how much work I can potentially get out, right? So that goes to my Helmholtz energy, right? So calculating that these changes in thermodynamic functions is of real interest that we care about. That's why we spend a lot of time talking about how to set it up, how to express these thermodynamic state functions, and how to express their dependence on temperature, volume, pressure, etc. And then later on, we want to further link these state functions into chemical potential so we can have a better description of material equilibrium, whether it's phase equilibrium or it's reaction equilibrium. So remember, when we're talking about chemical potential, the definition of chemical potential is a pretty long one, and people tend to make mistake here. So the full definition of your chemical potential of your species I in phase alpha. So we want to specify what is the chemical potential we're talking about. That is defined as a partial differential equation of the total Gibbs free energy of phase alpha. So this is where people always make mistake. It's in that definition of chemical potential. This is the total Gibbs free energy of everything inside that phase alpha. And divided by the partial differential of number of mole of your species I in phase alpha, while keeping temperature, pressure, and J naught equals to I in phase alpha constant. All right. And what's the physical meaning of chemical potential? We make a direct comparison of chemical potential in phase equilibrium into temperature, right? So chemical potential is an intensive function, like temperature is an intensive function. Chemical temperature tells you the direction of heat flow when you have two objects of different temperature. The heat flow from an object with higher temperature to an object with lower temperature. Likewise, chemical potential tells you the movement of your chemical species. Like in phase equilibrium, when you have a phase with higher chemical potential, it always flows into the phase with lower chemical potential when we're discussing phase equilibrium. And then we make a link between material equilibrium into reaction equilibrium using the generalized format of 0 goes to the sum of stoichiometric coefficient and your species I. That's when we start talking about reaction equilibrium. And for reaction equilibrium, we then went over in chapter 5 our table of thermodynamic properties. So these are the appendix table we handed out to you. So for entire chapter 5, we went over each of the terms inside the table, including like standard state heat of formation, standard state Gibbs free energy of formation. And then the conventional entropy, note that this is not 0 for any of the terms as long as we have a certain temperature. And also the standard isobaric heat capacity, molar isobaric heat capacity. So for the entire chapter 5, know how to use the table to calculate like heat of the reaction, delta G of the reaction. That's important. The other part that's important is know where these numbers are coming from. Right? Remember, we did that big example of how scientists measure the conventional entropy of SO2 with that long term, like a very long derivation with like 9 different steps of integration. That's how scientists come up with these numbers. And then we linked the things we calculated, like delta G of the reaction, delta H of the reaction, into kinetics of our chemical reactions. More specifically, well, not kinetics, thermodynamics of chemical reactions. More specifically, we link like delta G naught of a reaction at certain temperature to equal to RT ln Kp naught. Right, so here, my Kp naught is my standard equilibrium constant at certain temperature. We also went over the derivation of the Van 't Hoff equation, stating that's a relationship between, like, how does your equilibrium constant change with respect to temperature? So that we have d ln Kp naught over dt equals to delta H naught over RT squared. So for chapter 6, know how do we set up these equilibrium constant for ideal gas reactions, how to calculate equilibrium constant for ideal gas reactions, and, well, whenever the temperature is different from your standard thermodynamic table, how to adjust for that temperature change. So that's chapter 6. And then chapter 7 is phase diagram, right? So the phase rule, the one component phase diagram, and also the Capron equation we just did. And that's the end of our entire quarter. You see, like, even if things are sort of remote, we are using things we derived before, like the one we did, the one component phase diagram, right? You have like 3 points connected to each other. We can ask you to derive what is the relationship of Gibbs free energy as a function of temperature for those 3 points. And that is using these equations we derived before. So hopefully this gives you an overview of, well, I guess not an overview, a summary of whatever we discussed together in this entire quarter. All right, how are we feeling? Doing good? Okay, and then the rest of this document or the buffer lecture note is 3 different example problems, namely derivation problem, calculation problem, and then true and false problems. So that also represents the type of question we like to ask with a mixture of derivation, calculation, and also the true and false problem. I don't have time to go over every one of them, but I'll work with you to tell you, like, how do I think about this problem when I'm reading it without solving it to the full. You can check the annotated note to see how I solve the problem. For example, in this case, this is a typical derivation problem. It asks you to derive the partial differential of internal energy over volume at constant temperature for a gas that obeys the van der Waals equation of state. So in this case, when we're reading it, well, first of all, do we know what is this partial differential equation of internal energy over volume at constant T, or the volume dependence of internal energy? Right, so this is generally true. It doesn't matter what system we're looking at. In chapter 4, we went over the derivation of, say, the partial differential of U over volume at constant T equals to alpha over chi times temperature minus pressure. And here, alpha and chi are things we can derive coming from the equation of state. All right, so the equation of state, whether it's van der Waals equation or the PV equals nRT, that's a different dimensionality as these kind of relations. Okay, so in here, I'll be like, okay, so with the equation of state and calculus, we will be able to derive what is my alpha over chi. And plugging the numbers, we'll be able to solve for an expression of my du over dv at constant T. All right, so it's 2 steps. First step, reading it and say, like, do I know what is my du over dv at constant T? And second, in this expression, do I have a way to solve for my alpha over chi? And in this case, in order to solve for my alpha over chi, we need the equation of state. And the problem gives me the equation of state. So I know how to solve the problem. The rest is just calculus. We can take this one more step to say how to calculate delta U of an isothermal volume change of this van der Waals equation, van der Waals gas. So how do we do that? Let's say we have already solved this equation to equals to like nRT over V minus NB minus P. Just assuming you already solved it using calculus. The next step here, we're talking about delta U. So what is delta U? So my delta U is the integration of du. What is my du? And my du, you can write it as a partial differential of u over v at constant t dv plus du over dt at constant v dt. Reading the question, we're talking about the isothermal volume change. So this term goes to 0, and consequently, we don't care about your internal energy's temperature dependence. So my du effectively becomes this term, which is something we already solved. So we can write delta u equals to integration of du equals to this entire thing, nRT over v minus nb minus p dv. One more step here. Now, inside the pressure, it is a function of volume and temperature from the equation of state. So we have to write my pressure out as a function of volume and temperature. So my pressure from here, you can solve it yourself, but your pressure effectively equals to this long thing of like nRT minus AN squared over V plus AN cubed over B, V squared, V minus NB. All right, so plug it in. We then have this long integral that we were trying to solve. It's less likely I'll ask you to solve this integral. It's more likely I'll ask you to set up the integral so that we can plug it into a calculator and solve it. But in order to do that, you have to translate that pressure into a function of volume and temperature. Because we know that temperature is constant, right? But we want to translate this into a function of volume so that we can solve for it. And now if we look at this entire thing, now my N is a constant, R is a constant, temperature is a constant, volume is within my dV, so we can solve it, and B are all constant. In my pressure, same, N, R, T are constant, A constant, N squared constant, volume we can solve for, A, N cubed, B, these are all constant, V squared we can solve for. On the bottom, same thing, we only have volume minus NB. So we only have volume and some other bunch of constants. So we have a good way of solving this integral calculus. All right, so that's how I think about it when I see, and this is why we always work with ideal gases, because the real gas, sooner or later, the math becomes very nasty, but that's the reality. The chemistry behind it is not more complicated than ideal gases, it just math is becoming very bad. All right, so that's how I set up this derivation example. And let's look at the calculation example. I have 3 minutes. Let's see how we can do it. So we read this question together. No, ignore I tell you that, I'm not going to tell you this is from chapter 6, but we can read it and say, for a certain ideal gas reaction, we have the equilibrium constant, the standard equilibrium constant equals to 0.84 at 298 Kelvin and 0.125 at 315 Kelvin. The question asks you to find the delta H naught and delta S naught of the reaction. So what do we have here? First of all, we're looking at equilibrium constant, and the question asks us to solve for these, well, thermodynamic state functions of the equation, right? So obviously, we want to use the equation of the delta G naught at certain temperature equals to negative RT ln K. All right. Secondly, we see that my temperature is changing. So that's a hint of we should considering, well, my equilibrium constant is changing with respect to temperature. And for that, we're using the Van 't Hoff equation. And that is my d ln Kp naught over dt equals to delta H naught over RT squared. And when using the Van 't Hoff equation, we discussed that one of the hypotheses we're making is the delta H naught is constant when the temperature change is small, right? So that is the approximation we're making, that delta H naught is constant because my delta T is small. All right. And then we have all the tools we need to solve for it. First, we solve for delta G naught at 298 Kelvin using this equation here. And then since the temperature change is small, we can solve for the delta H naught. And then using the delta G naught, delta H naught, you'll be able to solve for the delta S naught. And for some reason, my pen is not working. But you get the gesture, right? So this is how I'm thinking about the problem and how to set up my calculation. Like it's a lot of equations as materials, but the take-home message for preparing of your exam is really think about the problem before you start doing the calculation in the wrong direction. Like take time to read the question and think about the question and use the correct way to address the problem before you start plugging the equation and solve for very complicated differential equations. I don't mean it. All right, so that's everything from me, and I hope you good luck with your study, and I'll probably see you next Friday or later today or this Sunday if you want to stop by for my office hours. All right, see ya.